This is the question that you got in the exam, okay? Including all these equations below. I gave you the equation of motion, the natural frequencies, and the mode shapes. So those first few steps you don't have to do, okay? It's a 3 degree of freedom problem this time, not a 2 degree of freedom problem. And I've got values for K, M. The force is being applied to the first mass and the last mass. F1 and F3 is 0. But then to the mass in the middle, we've got a linearly increasing force of 6T. And the question says, find the response of the system, x1, x2, and x3. So, obviously, I've given you the first 3 steps. And so your quest for this question is to go through steps 4, 5, 6, 7, and 8 of the modal analysis method. So the step 4 is finding the modal masses. Okay, so we apply the equation, the transpose of the mode shape times by the mass matrix, which is this one here, times by your mode shape, and you get the 3 values for each of the modes. Okay, mode 1, mode 2, and mode 3. Okay, and those are the values that we find. I haven't gone through the actual steps, the maths, because you can do that yourself in your own time. Remember, that's not what I'm assessing, but you should get some values. So we've got the modal masses. Once you've got the modal masses, you have to rescale using the equation of the mode shape divided by the square root of the modal mass. So for U1, we have these values. Okay, so that's this mode shape divided by the square root of this modal mass to get those values. Okay, for the second one, we've got the second mode shape, which is this one, divided by the square root of the second modal mass, which is this value, to get those values. Okay, and then the third mode shape divided by the square root of this modal mass to get this value, that rescaled mode shape. And then those 3 mode shapes lined up side by side gives you the modal matrix. Okay, phi. And that there is the key. So the next step is to deal with the forces, which is step 6. So for the forces, we take the transpose of the modal matrix. Okay, so the diagonal stays the same, but all the things that are off the diagonal swap places, times by our force vector, 0, 60, and 6, and 0. And so we've got this times by 0, plus this times by 6, plus this times by 0, which gives us the minus something times t. And then you go through the same process for each of those lines of the modal matrix transposed to get the values for the forces. So that's the form of the modal equation, okay? And we know that this is going to be some constant times by time, okay? And we know that we've solved mx double dot plus kx equals f naught time. So we then find the modal equations which are in this form, okay? And we match that up to our solution from chapter 3, which is here. And then it's just a matter of plugging in the relevant numbers. I've left omega 1, omega 2, and omega 3 as omegas in here. But obviously you could put your values in because I've given you those values in the question. Okay, so it's up to you whether you want to do that. That's perfectly fine. So step 8, which is the last step, involves applying this equation. We've got the modal matrix from the previous slide. You apply that to Q, Q1, Q2, and Q3, and you end up with this set of equations which represents the motion of the first mass, the second mass, and the third mass, the displacements of those masses in that system when you apply a constant force to mass 3. What happens? Okay? So hopefully by now you should have got a feeling of how you apply this. Okay? We've gone through a couple of examples. And once you get the idea, once you get the steps you go through, it's actually not that tough. Okay. The theory was a little bit challenging to start with. I understand it's a bit abstract, but the actual process that you'll be asked about for these sort of technical questions is relatively straightforward.